Hello, and welcome to our next presentation. This is day 3 of the final day of the symposium. And on behalf of the MIT CDOIQ Virtual Symposium, we would like to thank all our sponsors who have sponsored the symposium this year. Please keep a lookout for a very special survey that we'll be sending out shortly. In the meantime, let me thank our sponsors, Deloitte Informatica, Privacy Analytics, DAWIX, Fusion Alliance, KPMG, Santel Consultants, Tamer, Elation, Ali Data, Big ID, Boomi, Caserta, Citizen, Data Kitchen, Garage, Okira, Palog, Click, ThoughtSpot, Eckerson, Global ID, Snowflake, and Starburst. Please take a chance to go to Content Hub, see what content they have, download that, and if you get a chance, reach out to our partners. Without our partners, we would not be able to hold a symposium. Thank you, and we look forward to seeing you in 2021.
And good afternoon, everybody. This is almost the last session. I want to say last but not least and all that sort of good stuff, but it has been a very, very dense 3 days. And if you're like me, you're kind of overflowing with information. And yet we're still going to finish it up with an excellent session by my friend and colleague, Dr. Arka Mukherjee, who I've known for many, many years at this point. And he has been a tremendous supporter of this event and has created some groundbreaking technology and approaches to organizational data. And with that, Arka, I will simply turn it over to you.
Lovely. Thank you, Peter. And I will start my video. Let me know if you can see me. Peter?
Looks good. We see you perfectly.
Okay, lovely. And then I will share. I need to share my screen. So let me just move. I'm trying to move this panel so I can share it. All right. Let's see. Okay. Able to move the panel. I'm able to share my screen. And Peter, let me know if you can see my screen.
It looks good.
Okay, lovely. Well, special pleasure being at the MIT CDOIQ conference. I think I've been a part of this conference for many years, and I find this one of the best conferences around. I'm just delighted to be here. I've been listening to many of the presentations, and I have to say, all the organizers have done a spectacular job this year, as in all years. Special privilege to have Peter as the moderator, someone who I greatly respect. And Peter's been working in this area since the late 80s and carries a depth of insight. So it's a special privilege for me to have Peter as the moderator. Thanks again to everyone who joined in. If you managed to keep going till the last session, hats off to you. And hopefully we'll have a good session here today as well as we data lineage and traceability. I'm going to focus on the approach that we have been using for some time, and hopefully it'll be of interest to you. Certainly do ask questions if you're interested. So moving to what we want to discuss today, I'll start off with an introduction to what data lineage is and what kinds of problems are relevant to data lineage. I'll discuss why it is a difficult problem and why it has taken us a long time to make headway in terms of this problem. And then talk about environments, complex environments which require lineage and how we have attempted to about various outcomes that we have arrived at to show you what that if you do a data lineage project, what are the things that you get out of it. I'll start with a quick caveat. As I was trying to create this presentation, I was trying to keep it fairly independent of what our software does itself. Too many vendors and there's not too much work that has happened in this area, particularly because it is a hard problem. I should mention some of the other vendors in this space who do. There's Solidatus, there's Manta, and they are focused on the data lineage problem along with Informatica. And so we are delighted to be in that group of companies that are tackling these problems in this space. So some of these slides have come from Global IDs, but I hope that we'll try to keep it vendor independent and talk more about the problem than the specific vendor implementation. So I'll start with a little bit about myself. So I'm the founder and CEO of Global IDs. And prior to starting Global IDs many years back, I was working as a consultant. So I was exposed to some of these problems prior to starting Global IDs. And I got all my gray hair because I was trying to write the code for these systems. But and clearly, you'll have to be a judge of whether it actually worked or not. I do have a background in computational chemistry, so I do enjoy coding. So some of my professional interests are obviously the technology entrepreneurship role, where I have created startups and sustain them and scale them. But this has obviously been a very interesting journey, and so I enjoy my role as a technology entrepreneur. I don't have a boss, so that really helps me create stuff, whatever stuff I want to create myself. Um, and the second area is data ecosystem management, which we will talk about. It just talks about data from the viewpoint of what it has been in the past, what it will be in the future, and what it is in the present. And we are just delighted to be a part of the journey as we evolve data ecosystem management. I have other interests in the natural sciences and humanity, but a lot of my bias is towards sort of looking at these problems as being core scientific problems and linguistics problems. So I enjoy that, and then I read philosophy and history on the side just to keep my head in the right place. So some of my personal interests, I like going hiking, particularly to the mountains in the world. And so during my daughter's gap year, I took her to Mount Everest. And so you see Mount Everest in the background. This is the Everest base camp. And I took my son to Mount Kailash in Tibet. And this is on top of one of the high passes, around 19,500 feet up in the Himalayas. So this is the stuff that I do in addition to working on data management. A little bit about Global IDs. So we've invested in a very focused way the last 18 years in research and development in this area. So we are one of the vendors I find that are very narrowly focused on this set of hard problems, and has managed to retain our focus for some significant period of time. Obviously, these problems are very difficult and require that kind of attention. So we are happy that we've been able to keep our focus that long. Our core differentiators are scale, automation, as being the sort of primary focus, not just to solve the problems related to data management, but to do it at the scale of the largest organizations in the world. So we use things like semantic graphs and machine intelligence in order to bring about large-scale automation. The analysts have been fairly complimentary about us, and our implementations are in the world's largest companies in multiple sectors of the market. So we are, once again, without our customers, we would be nowhere. And to those of you in my audience who are part of our customer community, many thanks to you. So what is the aspiration of Global IDs has been always to sort of think of data as math, right? So math and physics. So like in the physics world, all matter and energy have been essentially reduced to a set of equations that everyone can understand. Similarly, our aspiration is to look at data management and say that here are the different components of the system, and the system has a certain amount of velocity and acceleration. that tells you what the system is doing and why it's important. And our job is to actually just make things fit into these equations. So we've made significant progress over the last 18 years. There's some ways to go, but we believe that this presentation, where we're really talking about lineage and velocity, takes us sort of so in terms of the middle point of what we are aspiring to do. So let's. I gave a fairly long introduction, but thanks for bearing with me on that. Um, the so what is data lineage? We'll start with the definition. The simplest definition is the flow of data across a data ecosystem. All data originates in some upstream system, and then as it is replicated and copied and transformed and moved in across the environment, it flows just like water flows from up in the mountains into tributaries and pools and lakes and eventually into the river and into the ocean. Data has that kind of path as well, right? So our goal is to sort of reverse engineer from the systems environment what this flow is, and essentially how things change in time and space as it moves across the environment. So in order to do this, we take a very philosophy and ontology oriented approach. We say, what are the parts of the system, right? So that would be individual data assets that exist across the data ecosystem. And what are the relationships across these across these parts? And then what is the change over time, which is essentially the flow. So when we look at data lineage, this is what we are trying to gather: parts, relationships, and then change or flow. So why is data lineage such an important problem? And so if you look at the left-hand side and you look at the diagram that talks about data lineage, right? So before data lineage, you have a whole bunch of systems in your environment. It could be hundreds, it could be thousands, it could be tens of thousands of systems across the environment. And there's some connections between them, of course, but these things are very poorly documented. So more or less, all these systems and applications are standalone, independent systems. Now, our goal in data lineage is, of course, to say, well, I want to understand how customer information is flowing, or trade information is flowing, or loan information is flowing, right? I need to find all the arrows across the systems and the temporal movement of the data across those systems. So, because once I understand that kind of flow, that I've been able to decompose these systems and say that there's individual logical objects are moving in this particular way across the data environment, there's a lot that can be done. Clearly, you can say what data is being used and which systems and which applications are using it, right? So problem of data usage becomes solved because the data that is moving at velocity and is being individually consumed along the way, it gives you computational ways of looking at data usage. Second is you can look at data quality. As it's flowing and as it is moving across the system, there are transformations that are happening along the way. And so as those transformations are happening, are errors being introduced into the system, meaning are errors being introduced in the points of origination during the flow process itself. So for data lineage is great for data quality, and we'll give some examples further on. The part that I would say is that ultimately, if you have data lineage, you can construct graph-based solutions. So graphs are the new ways of looking at data. It shows all the parts, all the relationships, and potentially all the flows. So much of the work that we've been focusing on at Global IDs is to take the parts, the relationships, and the flow, and put it inside graphs, graph environments, and we are very happy to work with a number of graph vendors like Cambridge Semantics and Neo4j, in order to take all of this information and put it inside graph structures, because we feel that those kinds of structures can show lineage quite well. So lineage is important for quality, for usage, for impact analysis, for understanding of transformations. There's a whole variety of reasons why lineage becomes important. For our business, it has turned out that the regulatory requirement has turned out to be the most important use. So essentially, the regulators who are looking at downstream reports, and they say, where did this data come from? Validate that the data is actually true and that somebody didn't cook their books. That has evidence, scientific, incontrovertible evidence about how data is moving is very important to the regulators, and we try to satisfy that goal. That has become an important goal across many industries. So I'm going to just show you a video here in terms of the end state. So let me just play this video. And we are talking about lineage and traceability. So where we are talking about lineage and traceability and what happens. So in this screen, we are essentially looking for a particular customer ID and says, this particular customer ID, how's it flowing across the data ecosystem? So we can see a whole bunch of applications, and we can see that customers, orders, products, individual products. This is the way they are flowing across the data ecosystem. So there's detailed, granular visibility into how data is flowing. There's timestamp information along the way, and one is able to then look at individual granular piece of data and say, this is how it's flowing. As it does that, as you can see, the diagram on the left-hand side shows the flow of information, and one can dig into the arrows and drill down into the arrows and look at a variety of data quality problems along the way. So you can essentially take out the individual threads that compose the flow, so the tributaries, so as to say, the tributaries across the system as they are flowing into the lakes and into the rivers. Each tributary can be tracked, and each tributary's characteristics can be looked at. So that's sort of an example of how data lineage and traceability can be done, where individual values can be tracked across the whole entire ecosystem. So moving into the next slide. So in order to construct that kind of end state, right, what are the challenges? So clearly, the challenges are, okay, I need to look at my customer IDs and my product IDs and my invoice IDs, etc. Where are they in the ecosystem? Because the data is largely unorganized. It is not tagged properly. There's no standard naming conventions. And as a result, you can't find the data that you want. So first you have to have some way of organizing the data so that it's everything is in its own bucket, and it's has the right semantic tags associated with it. The second problem, and in order to do that, you have to do these large-scale scans, which if you try to do that manually, the costs are just extraordinarily high. So yeah, they're very high costs in terms of generating lineage manually. And then, of course, because if you try to do it manually, then the process becomes slow and cannot work at scale. So semantic disorganization, time, and cost of delivery make data lineage a very hard problem. In order for us to solve the problem, we've tried to sort of address it in 10 steps. So the first step along the methodology that we use for data lineage is related to sort of having a glossary of what are the things that are important to the business. We semantify that glossary and create a taxonomy out of it. And then out of that, we say, all right, these are the things that are important for the organization. Let us go and scan the environment and where this information exists. So we go through this automated metadata harvesting process at the scale of thousands, tens of thousands of databases, and we are able to get a full inventory of the entire ecosystem. Once we are doing that, we do detailed statistics analysis on all data assets that we found in the inventory. So everything gets documented, and a profile exists with everything inside that environment. So now come the hard steps. So far everything that I've described is relatively trivial, but the classification and the next step, which is the mapping step, these are really hard steps. I need to look at millions of data assets, or make it too complex. Let's say even thousands of columns of information, and say where are my customer IDs, and where are my where are all my critical data elements across this complex data environment. So I have to classify each column and put it into its right semantic bucket. Here are my customer IDs, here are my customer names, here are my customer addresses, here are my customer SSNs, whatever, right? And do that for somewhere between 10,000, to 20,000 business critical data elements. Right? Not all of them are critical, but at least some portion of them are. And this ability to classify at a large scale becomes difficult. So we've been struggling with that problem for 10, 15 years. And we realized that the rule-based approaches that most vendors use are inadequate for those systems. And so we need to go into this problem with machine learning, and we'll demonstrate some of this today. The part is, of course, to mapping the objects. Where are my customer objects, where are my product objects, where are my loan objects, where are my objects, and so the classification and mapping becomes the heart of the lineage problem. Because once you do that, next you can tackle the lineage problem. How information is flowing, and how individual data elements are flowing across the system. And with that, you can get a good sense of quality, and you can do your analytics fast, because now you know where all your data is. Everything is semantically tagged. Now you're in a position to do analytics. So we use this 10-step methodology that in order to, and for today's conversation, we are really focusing on these parts, the lineage, the tracing, and the quality parts. But hopefully that was a good way of introducing the topic, and telling you sort of all the larger components of the system as we focus on just the lineage and traceability problem. So over time, we've experimented with a lot of different ways in terms of trying to reverse engineer the lineage out of the data ecosystem. And what we realized that there are certain approaches that are, appear like a good idea, but actually are not. So after a lot of experimentation, trial and error, lots of failures, we've come up with a very pragmatic way of dealing with the problem of lineage. And essentially it translates to, you have to have a logical to physical map of all the data that's flowing, that's in the system. So just knowing the inventory or knowing the catalog is not enough. It has to actually be generated into a map in terms of the way the company does business. So without that, you can't make any progress. Right? The next part is to generate hypothesis of how data is flowing. There are certain patterns inside the data which would indicate that data is flowing in this particular way. And so you generate hypotheses. Hypotheses can be generated in many different ways. You can scan in ETL code, you can scan in stored procedure code, you can scan in a variety of different mapping tables, you can scan in a whole bunch of things, or you can get people to draw arrow lines and arrows on diagrams and get them to generate the hypothesis. But each one of those things are just hypotheses. They are potential flows, they are not actual flows. So GlobalIDs at that point says, okay, based on all these hypotheses, just like a scientist would approach this and say, okay, we have a variety of hypotheses, which ones are true and which ones are not. And so the third step is really the validation of the hypothesis purely based on the data itself. We are looking at the data and we say, yeah, this flow is happening, or no, that flow is, somebody made a mistake, it cannot be happening. So we want to convert this into, there's no controversy about each of the lines in your data lineage flow, and each segment of your data lineage flow is backed up with data. And so once you have validated the end-to-end flows, then there's reporting and visualization that supports it. We have a number of white papers on this in case anybody's interested. So let's look at each of those steps step by step, right? So look at those 5 steps in more detail. So the first step is the first step is trying to get the logical world, the business world, mapped to the physical world or the systems world, whatever is in my databases, right? So if you look at the approaches that have been used before, right? So we focus on the bottom up approach, right? And then there are other technologies that focus up on the top down approach, right? So there's the bottom up scanning, right, where we use machine intelligence to essentially reverse engineer the whole system, right? And look at all the data assets across the whole data ecosystem and say, here's a full physical inventory. So that's the bottom part. And then a variety of techniques can be used to get the logical part. Essentially asking, what are the things that the business actually runs on, or what's important to the business, and what should we be tracking in the business? Things like customers and products and a variety of different things that are related to the business, right? So employees, suppliers, warehouses, locations. So you can go through it. These are typically largely categories of master data and reference, but then almost everything that you find in your data warehouse that is going to be analyzed is also a part of that business model. So the logical model or the business model comes from top, and what we do, and then construct a knowledge graph out of it. Right? So this is how the mapping of physical and logical concepts happen, and just some of the steps that we use in order to get there is first do this deep statistical analysis of all the every data asset that's in the system. So in many of our customers, particularly large customers, we have 10 million, 20 million, 50 million, 100 million of exactly these kinds of analysis done at the columnar level, right? Just to understand sort of from a statistical perspective what each of these assets actually mean. What is the underlying semantics related to each column in the data environment. So once that process has been done, once again, very hard to do humanly, but easy for a machine to do. So you can get full visibility in terms of saying these are all the data assets across the ecosystem. The next part is okay, how do I now say what each column means? How does, when I look at a particular column inside a table, inside a schema, inside a database instance, inside an application, that column, what does it mean? Right? So over the last 5 years, we built the machine learning capabilities, which allows us to essentially, instead of coding rules and say this is what a customer ID means, we say, all right, let's just teach the system. Right? And so we teach the system by pointing out examples of what a customer ID is, and then the machine takes over by itself. Right? So for each business concept, we go through this training session, and with a few, a little bit of training, maybe under 15 minutes, the software has constructed a classification model that would allow us to go and say, we've got a converged model. We understand what you mean by this particular concept. It's a very, very powerful approach. And we believe that using that approach, you can take a complex data ecosystem and say, this is how you do your business, right? These are all your critical data elements, and it's resolved into into models that the machines can run on a continuous basis, and you always know the data that you're dealing with. So this particular screenshot itself is representing a part of our software, which essentially says, this is, I'm looking at a particular concept called an account number, and that with 19 clicks, 13 positive clicks and 6 negative clicks, I've been able to locate 95 predicted columns and 186 candidate columns. So with a very little effort, right, I've suddenly sort of put a predictive net across my entire ecosystem. So these things are, we can get accuracy to a very high level as a result of this. So here's a quick video that shows how machine learning models can be classified. Let's see. Okay. We take the, we want to demonstrate how a particular model is. This is something that we have done with our prospects. You know, they wanted to know what a FDIC certificate was. We have no idea what an FDIC certificate is, but we create the concept, and we over here we provide some feedback, you know, some yes/no feedback about what is an FDIC certificate number, and the model trains itself. And with every yes and every no, you can see that we got to a 90% accuracy in creating a FDIC certificate model, right? So so we have not coded any rules. We have no understanding of what this particular concept is. But just like you train a child by saying, "Yep, this is a ball and this is not a ball," suddenly the child understands what the concept of a ball is. We here have trained the machine to say, "You got you know, we've told you what a FDIC certificate number is, and so you can." Now the machine understands the concept, quote unquote understands the concept, and so as a result it can this happens in minutes. So all the concepts that you want to track, you go through this exercise, and you know every place in the data ecosystem where that concept lies. So the models have accuracy, and the confusion matrices that says these are the true positives, these are the true negatives, and yeah, these are the false positives, false negatives, and all of this, the converged model, all of this gets resolved into true positives and true negatives, and as a result, you can really get these models to be of a very high accuracy. When subject matter experts come in, they can go into any ambiguous parts of the software, and they can provide additional feedback to get a higher accuracy level. But as a result of all this, yeah, one can take objects and say, okay, these particular objects are found across these parts of the ecosystem. So I think in this diagram, the object is mentioned on the left-hand side, so these we can say that these are the variety of applications that have these objects, and so a mapping can be done in a largely automated way. So if you ask yourself, I want to say, for my KYC purposes, I want to know where all my customer related objects are across my whole ecosystem, every application in my ecosystem. The software will essentially be able to now sort it out because you have done the logical mapping. And so this is a very efficient, granular way in terms of how to establish maps. Now, maps, of course, are not lineage. And so this is just, as I said, you built the foundation on which lineage can now be solved. But without the classification and the mapping, making any progress becomes very, very difficult. So I think this is restating the point, but the implication of all this is that classification, uh, classification, semantic classification is essentially the foundation of data lineage, and that you know semantic classification is only possible at scale if you use machine learning. So that was the first step, right? I've done my mapping of all my objects on the basis of how I do my business. And now I'm going to generate a variety of hypotheses about how it's flowing across the system. So essentially what we are talking about is we are talking about temporal movement, right? So there's a timestamp associated with anything that's moving, and that we are looking at data, temporal a movement across the environment. We, so here's a simple example of what a flow segment hypothesis is. So once again, this is a screenshot from Global ITs. So it just says we're going to do a survey, right? And we're interested in knowing how credit data, right, is moving across applications. Can you tell us whether it's flowing in or out? And so flowing in and out, and so out of the system. So people may not understand detail level flows, but application owners generally have an understanding of how high level flows are happening. So just through survey based approaches, one can get a high level flow of the environment. So that high level flow then uh, translates to more detailed level flow. These things can also be generated on a manual basis by people drawing arrows across the environment. So I know that this particular column flows from this application to another application. So I could draw a line and say, this is a hypothesis of how data flows based on my experience. Once that is done, so and you've created a hypothesis, you might have obtained other hypotheses through ETL scanning or stored procedure scanning or a variety of other scanning methods. It says I have this flow, and I have a potential flow map of how data is moving for these set of logical objects, right? So so I have now a potential flow which I can either validate or invalidate. So we're following a scientific technique here. We are essentially saying, whenever I say I understand something, I construct a hypothesis, and then I either validate it or invalidate it. And so that's what I'm going to do in the next steps. I'm either going to validate or invalidate each of the arrows that you see on screen. So the implication of this is, once again, you can construct hypothesis anyway. You can dream it up. You can use it on the basis of your experience. You can use scanning of a variety of different ways, and you can generate lots and lots of hypotheses saying this is how I think data is flowing. Right? And the next step then becomes, okay, what's true? What is correct? Where is evidence for each of these flows? And so as we go inside each map that has been constructed, we say, all right, let the system go and look at the underlying data and see if the data if indeed there's flow or not. So it turns out that most of the arrows that are in red are showing flows that are invalid. Right? For some reason, they were introduced over there, but it turns out that there is no flow that's happening, and it's only the green arrows where the flow is actually happening. So now I've taken the hypothesis and validated some parts of it and invalidated other parts of it. But I have a mechanism that cannot be challenged anymore because it's all based on underlying data. And so this could be the validated hypothesis for each segment. And so now I have only green arrows that show me where true data flow is happening. And this can be then sent into some kind of reporting environment. So based on our experience, one can look at segments of information. So you might want to say that, look, I want to look at just my customer data, how it's originating, and which systems its applications is flowing through. What are the intermediate systems? What are the downstream, maybe data warehouse systems or master data management systems? And then these are the reports that are being generated out of those systems. I want to look at the flow end to end, and and all steps along the way are being validated through the machine. And so our suggestion to our customers, again, our practical experiences, essentially, you can take each critical data element and go through this process, or you can take each critical data object and go through the process. But at the end of it, you actually know, with a fair amount of evidence, how the information is flowing, and what evidence is backing it. Interested in downstream systems and how you got there, there is evidence to say this is how it got there. Once again, more descriptions on sort of the end-to-end hypothesis, where you can actually go and drill down into each of the arrows and say, yeah, what is the evidence? I haven't provided any information over there, but would be happy to talk to you if anybody was interested. So the last step is the visualization and the reporting. This is sort of describing some of the evidence that is being collected. So I'm looking at a source, and I'm looking at a target, and I'm looking at what is the overlap from a Venn diagram perspective, a temporal overlap that happens across the systems. And so from these kinds of reports, this is what we call incontroversial sort of evidence, and so very strongly validated by the system itself. Now, we'll end the presentation on the basis of the outcome. So I'll describe some of the outcomes that we go through this exercise, and we say, okay, what is the outcome? So the first outcome, of course, is you have a mechanism for understanding lineage across the entire data ecosystem, right? That you want to look at the flow of certain business objects as they're found in all your applications. Well, this approach gives you a pragmatic way of solving it. It is not, it is not compute everything out of a data lake, right? It's not that. It is, the approach is very pragmatic and says, while those things are theoretically possible, they are fraught with lots of other problems, right? And cannot be solved at scale. This approach says, we don't care how many systems or how complex your environment is, but there's this pragmatic way of involving both humans and machines to solve the lineage problem. And at the end of it, every object that you're interested in, you can track across your systems. The second outcome is, of course, the impact analysis, right? Many of our use cases involve organizations that are trying to change their old systems. They have these legacy systems that need to be modernized, but you're afraid to touch any of those legacy systems because you don't know what is going to be impacted. So what Global IDs does, or what our software does, is essentially to say that we can understand the impact of touching this particular application. Here are all the other applications that are going to be impacted if you touch this, right? And so for modernization initiatives, right, this is essential. You want to shut down a particular system, you need to understand what is being impacted. And so, from an impact analysis perspective, this kind of incontrovertible proof is very, very valuable, and many of our customers go down this route. I've already mentioned the regulatory reporting requirements, where we are looking at a variety of regulations with our financial services customers. We look at the many of the credit risk and liquidity reporting requirements, uh, part of the Basel requirements that most companies, most of the large CFIs have to adhere to. And so each of those things are broken down into narrow parts, and then the it's by resolving lineage on the narrow parts and then aggregating them, you can have the regulatory requirements being met. And then so that's sort of the presentation, and I've walked through the what, why, and the how of it, and we have, I guess, Peter, we have a few minutes left.
Absolutely. And question queued up for you in the chat, or I can read it to you. You tell me what's easier for you, Arka.
Feel free to just read it out, and I'll try to answer it the best I can.
Very good. The question is, I believe the goal of data lineage is 100% reliable traceability of data. That seems to be a statement. The question, can you comment on how you achieve this level of trust based on ML-sourced hypotheses?
No, so I think 100% is always a difficult goal in anything, right? So 100% can never be achieved because data environments are very, very complex, right? And you don't know anything with surety because there's too much noise in the system, right? So let me first address the problem of the 100%, and then the problem of whether machine learning is capable of addressing how much of the 100% problem can actually be solved by machines. So in our experience, what we've discovered is that that for a variety of historical reasons, mainly the fact that in 30 years back, storage was very expensive. People have taken all kinds of shortcuts in terms of representing the data internally. So the data that's in there is not sufficient to provide the evidence. So let me give you one practical example of that. So when data is moving, you need two things. First of all, you need data overlap, and then you need temporal overlap, meaning on both sides you have to have a timestamp, right? But historical systems have often ignored the timestamp because they want to save on storage costs, right? And as a result, the timestamps don't exist. So what to do? You don't. There's no way of knowing the directionality of the arrow that connects any two source and targets together. So in those particular situations, we have to go through a variety of tricks in order to create the temporal direction. There's one particular method which we call the stroboscope, which by placing an artificial strobe on the system, we are able to compute the timestamps even if they don't exist in the underlying database. So by using sophisticated techniques like that, we think that we can understand sort of the flow of the information. Okay, so that's sort of one problem, the absence of timestamps. The other problem is in much of the data, most of it is signal, but a lot of it is noise. And filtering out what is signal and what is noise is always very difficult. And many people say that that's the data quality problem in the system. So we have to figure out all the rules that allow us to take the noise and get it out of the system, right? Or at least tag it such that the system doesn't pay attention to it. So now, since those rules are not going to be ever going to be comprehensive, or it's going to be difficult to make them comprehensive, there's going to be some noise in the system. Get to that 100% accuracy viewpoint. So those are two kinds of problems. There are other kinds of problems. There are many other kinds of problems which get. Some of it is we don't know what the underlying processes are, and we don't know the underlying logic of the code that's moving data. right? So to the extent that we don't have visibility into the process layer, it creates another variety of uncertainty. So based on all these uncertainties, the 100% goal is not, we don't even aspire for the 100% goal. The goal in our mind is to get it to a point where it's at least above 90%, right? So somewhere in the 90 to 100% range is what our aspiration is. In many cases, we see that. In some cases, the rule-based approaches are all stuck at 30%. It's less than 30% accuracy in rule-based systems. Our goal is to bring it up to sort of close to 90%. We believe that we can get it to 90% if we apply some additional tricks from our bag of tricks in order to address the deficiencies of the system. So that's a long answer. Hopefully, it was an accurate way of saying that 100% 100% lack of controversy is not possible. There are a variety of systemic problems which pervade these data ecosystems that cannot be solved right now. So our goal is to get to 90% with evidence that the 90% that we've got is guaranteed. Right? So that's all right, Peter. Hopefully that answer was not too long-winded, but
goodness, no, it's a very nice dissertation around that, and actually, I want to pull that thread question, and that is to say that I think one of the other things you've hit on here is something that has not generally been recognized in the AI/ML. By the way, you got a thanks for the answer, so it was appreciated by the questioner. Thank you for commenting on that. But what we're seeing right now is that literally the learning algorithms are running out of good data, and the data that they can get becomes in many ways flawed because it's biased, because it's very difficult to create data of the type that is needed to truly train things unless you're working from a series of facts. Now this, of course, hits at your and my passion, is the goal to go in and find out what is at the root of many of these systems. But when you're talking about using ML, it's not just the generic, we're doing ML, which, as you said, is achieving 30% rates, which is nowhere near enough lift to get off the ground. But by working directly from the factual information, you're able to, just leapfrog the amount of trust that you can put in it, because when somebody says something to you, your answer is generally right click, right? And I can show you what it is that we're talking about down there. And I think it's important to highlight that aspect of the work that you're doing, which is just a fraction of the whole ecosystem that you're developing in here. But maybe you can comment on, have you seen anybody getting traction around these learning algorithms outside of what we're doing in this area?
Yeah, so Peter, I think you've hit the nail on the head. Many of these AI systems are hybrid AI systems, right? That are being discussed at the conference. I attended a very nice talk by Osama Fayed early on in the conference, where he talks about this, right? He says that, to do ML and AI properly, you need lots of data, right? And where can you get it? Well, if you hand it a couple of spreadsheets, it's really not going to be able to do a good job. It needs lots of data. So our approach, where we are actually looking at the whole ecosystem, gives us a massive amount of data, right? So in one of our larger customer environments, we have something like maybe 500 million columns of information. We think there's going to be probably 1 billion columns of information, right? And so we can generate feature vectors, at a massive scale in the billions level, and so the machines become much smarter when that much data is handed to them, right? And so we think that that it is absolutely true that AI systems and machine learning systems are really hungry for data, and there's not enough data available in order to address these problems. But once you're looking at it at the ecosystem level, at least we've seen that there's no paucity of data. So if problems are attempted at that scale, then perhaps there is enough data. Of course, it introduces a whole bunch of new problems, because just access to large scale data is very, very difficult. People tend to hoard their data. People tend to control their data. There are valid security systems for preventing security reasons for preventing access. So, but assuming that you can clear those hurdles, and we've cleared those hurdles in some of our customers, we are able to address the paucity of data issue and have enough information over there to go down this path. But there's not much ambiguity. At that point, the machines are much, much better than humans. I mean, like Peter, you and I have been working on data management for 20, 30 years now.
Mhm.
And I can tell you that the machine is much, much smarter than me. May not be as smart as you, but
Oh, no, I agree with you 100%.
but I can see just magic happening once the learning algorithms have been converged.
I guess I'll just make again, anybody has a question for Arka, please chime right in. It's a free channel right now, or lines are open, I guess is what you say, right, Arka? Remember those days when we used to listen to radio and things like that? Anyway, when we look at what, go ahead.
No, I think, Peter, maybe the question should really come from you, right? Because, I mean, a lot of the direction that we went down was some of the early books that you had written. In fact, I keep telling people the story about how I discovered your 1989 book on reverse engineering data, right? Which is, of course, the path that we started. But we started in 2001, about a decade after you had published your book. So, as you look at sort of the solutions that we have proposed over here and what we have solved over here, what do you think are the deep gaps that remain as well?
Well, I'm not going to address technical gaps at all because I'm not qualified to do that. But I look at as capabilities, and there are amazing things to be learned when you look at an organization. Just very simply, 20 to 40% of all IT costs are wrapped up in unnecessary transformations to data that keep occurring because nobody's keeping track of things. So that's kind of like the old days where you used to go around and say, I'll do server consolidation for you. And there were people that made tons of money in that area. I'm just amazed that people aren't picking up on it. Literally much opportunity out there, both for the organizations to get better, but also for organizations to help with that process. So what I'm working on right now in Arka is a literacy, hopefully contribution. And it really turns out that organizations that want to do anything meaningful about this need to look at their knowledge workers. We did this 2 panels ago. So obviously this is my nth one of these we've done on the track, but here we've got a fantastic situation where we're preaching to the choir, and it's wonderful that we're exchanging this information. But I was just trying to take a step back and say, who outside of our group of people that we like to associate with and hang out because we all speak the same language would understand anything that just happened here? And it was just a very nice articulation of why standards help organizations save money, right? I'm sorry, I'm babbling here, but
you're really right in the sense that cost and complexity are going to drive everything here, right? If systems become so expensive that you really don't have an innovation budget left anymore, that your business as usual budget is just used for keeping the lights on, obviously you can't create competitive advantage. So the idea here is that all that legacy that you have on your as baggage on your back, right? There have to be ways of getting rid of that baggage and creating new systems that are far more efficient and far more modern. Right? So the lineage and traceability solution allows you to get your get rid of the baggage, right? And say any modernization effort, we need to know sort of the dependencies. This tells us the dependencies. Now create new systems, perhaps on data lakes or perhaps on the cloud, that allow you to shed the old baggage and create modern systems. So on that note, we'll leave it. We have.
Thanks. Yes, perfect.
Yeah, Peter, thanks so much for your guidance as well, and for your the moderator role. And I appreciate everyone who hung around till the end of the conference and spent time with us today. Appreciate it.
I appreciate it also.
Yeah, take
Arka,
care.
there were a couple more questions. I'll put them in an email to you.
Okay, lovely. I will address them over email then.
If possible.